And we head over to the next talk by Edward Fagan. Yes.
All right. Hello, everyone. I can see you're all on the edge of your seats. Certification will do that to people. All right. So let's get into it. I'm going to talk about the certification landscape and really kind of following up from what Christian was good enough to just kind of give the background to. First of all, I suppose certification as a concept, we understand that it's about verification of the requirements that are set out for the processes, products, systems, and people involved in creating airborne wind energy systems in our case. Really, what we wanted to get to with our project was kind of a side-by-side comparison between aviation and conventional wind certification schemes. And the reason is that each have their own aspects that deal with what we have in airborne wind energy systems, as kind of Christian walked through. And each industry's requirements, rules, and processes are quite different. There's different organizational approvals, different certificates, and ultimately the supply chain for each of those industries adhere to those rules. So if you're drawn from each supply chain, you're going to have you're likely to come into contradictions and just different processes. So we wanted to kind of compare side by side and understand where they are similar and where there are gaps. All of this is part of Work Package 5 of the Hawk project. So some of you might have already heard of the Hawk project mentioned. It's funded by the Sustainable Energy Authority of Ireland. I'm a collaborator on the project. Airborne Wind Europe are as well, and it's led by teams in the University of Galway and CTL in Ireland. As part of this work package, we set out to kind of create that roadmap to certification, look at what the major deliverables and milestones are, and identify the risks and trade-offs for each industry's approach. But we're really narrowed in on the composite aerostructures for rigid wing aircraft. That's kind of the overall focus of the project. So I won't dwell on this since Christian's done given a nice overview already of the obstacle versus UAS sort of goal of certifying airborne wind energy systems. But just to say that we wanted to start off by identifying what the bodies for certification, the standards are, and the rules and regulations, and identify for airborne wind energy systems what ultimately does that mean. What are the standards that we need to start comparing? And as Christian mentioned, there's a desire out there to be regulated in the IEC approach and the IEC 61400-80 that is being assessed, or as a sort of a framework for going forward, is that kind of process is what we followed here in this work. So just to set a bit of background, in terms of a roadmap, we want to look at the sort of risk and maturity levels for the airborne wind energy systems of different sizes, and we split them out like following the Airborne Wind Europe approach with pre-commercial or current systems that are in development, early commercial systems as we start to scale up in sort of size and risk and maturity, up to fully commercial systems on the right. So what does that mean for the actual type certification process, and how each industry approaches certification? So I'm not going to step through the flow chart here. I hope you can see it okay. I might have made a miscalculation in terms of the color profile on the flow chart, but what I've set out, the main things to look at here are the light kind of greeny blue stages in the wind turbine type certification process and how they interact with project certification. So after you've done your preliminary design on your system, you move into type certification, you get your TC awarded, and after that there's a type certificate maintenance process. So every 3 years or 5 years you do a bit of an update with the IEC representatives to show that your system is still working, and if there's any issues, you've addressed them. In the meantime, you're getting into project certification for the actual wind farm and maintenance of that over the wind farm's lifetime. Process is a little bit different for civil aviation. So you still have your preliminary design, then you start into both type certification and the design organization approval process. You get the DOA approved first, type certificate comes second. In the meantime, you've got your production organization approval process, and down the bottom, the kind of equivalent to a project, wind farm project certification, you've got all these airworthiness certificate groups and approval processes that have to happen for maintenance, continuing airworthiness management, the actual air operator, all of these different groups. And just as a summary, we have sort of a list or a table on the left, and for the wind energy approving bodies and certificates that you need to get, and showing who's basically responsible for as an applicant, whether it's the supplier, the integrator, or the operator. And on the civil aviation side, you have similar product certificates versus the organization approvals. And you can see I've included here the FAA, EASA, and the National Aviation Authorities, how they're split out in terms of responsibilities. What does that all mean for a roadmap for airborne wind energy systems? So as they get further and further towards commercial operation, and kind of in the y-axis as we look at moving towards more and more certification, sort of this first step up here, it's not overly clear. You've got the kind of current regulatory sandbox where on the civil aviation side you're looking at SORA, Sail 2, permits to fly, but no type or project certifications. In the middle, we're getting up to early commercial, and as part of that roadmap you might want to look at prototype type certificates for the wind turbine side, or the equivalent is kind of a restricted type certificate process, and moving up to Sail 3, but continuing with the permits to fly. Full commercialization then, is it ultimately the type certificate and project certificate route that we want to follow with the IEC guidelines. Kind of digging down into detail now, really that was all background. We want to understand the processes from each industry, but really we want to dive into what type certification actually looks like, or might look like for airborne wind energy aerostructures. So the two flow charts here show the overall process for type certification. The one in the left-hand flow chart just shows that for wind you're moving through design basis, kind of generation and evaluation. They're evaluating your actual design, going through manufacturing and testing evaluations, and your final evaluation gets you your type certificate. But it's a really modular process, so you're getting conformity statements at each of these phases. On the civil aviation side on the right, you've got really a similar process. You set out your working methods, it's like the design basis. Your certification basis is evaluated, like your design evaluation. Then it gets a little bit fuzzier. You've got a certification program, has to be defined and agreed with the aviation body. And phase 3 is really the big one, where you're getting into compliance determination. And ultimately you get your type certificate out of that. What we wanted to focus on for Aerostructures is sort of doing a gap analysis of the different standards, specifications, and means of compliance that are up at the very start. So for the phases using the IEC approach, the design-based evaluation, so if we go back, it's the very top left box in the left flowchart. That's broken down into kind of a whole bunch of different phases. The first one really being identifying the codes and standards you're going to use, what your design parameters and assumptions are, and your design methodologies and principles. So on the aviation side, that could be drawing from CS23 for light sailplanes. I should have said at the start, my background actually was with Ampix Power, so some of this work started with what Ampix were looking at in the development of their CSAP certification specs. So that's kind of what we looked at here, CS23 for light sailplanes, and the acceptable means of compliance document for that is AMC 2029. So that all relates to kind of everything on composite aircraft structures. The comparable standards then on the IEC are the 61400 series, and within that there's a whole bunch of different parts that all have aspects of composite structures related to them. The standard at the very bottom, this DNV one, is a nice reference point because it kind of combines everything from the IEC standards that relate to wind turbine blades, and it's also free. So it was a handy one to start at for investigation. And just to give a bit of background as well, this isn't the first time this process has kind of been started, this side-by-side comparison of the two industries. Some preliminary assessment was done by DNV, were hired by Makani back in 2018 to look at this. It's a little bit fuzzy, just the spreadsheets that they included as a PDF. But what they've done is walk through really high-level components. So in the wings and planform section, they've just identified wings as a major system, and identified the IEC 61 standard, and kind of classified the problem, whether it was a known technology or unknown, and what the general gaps were. We really wanted to go kind of a level past that. So on the left-hand side, we had the IEC standards, well, IEC/DNV, and we're actually starting to map specific sections in each standard between the wind side and the aviation side on the right. So blowing up what was in those little tables of contents, we identify all the paragraphs and subsections on the IEC side that relate to something like material properties, and we match them up with the subparts and paragraphs in the aviation side that deal with all the same topics. So it's a big job. There's several hundred pages of documentation to go through on each of those 4 documents, or 5 if you expand out the IEC ones. And but for major topics, we look at how they all compare. And really that comparison boils down to, what we're using the IEC as the basis, where are there wind turbine gaps that need to be filled by bits from the aviation standards, and ultimately what's the considerations that need to be made for airborne wind energy systems. A few just initial findings. I'm almost wrapped up here. On the design side, the aviation industry uses or recommends a damage tolerant design approach. In the wind standard, it's really quite different. It's material knockdown factors, generally based on statistical analysis of failures of different components. That sort of damage analysis approach also goes to the types of failures. So what do we have here? Oh yeah, so on the wind side, it's fiber failure, interfiber failure, buckling, but aviation is kind of more generally interested in characterizing damage growth, and a lot of that comes from impact damage. So that's an area that is going to need to be addressed. If you're following the IEC standard, you're going to need to understand the differences and kind of have a methodology for how you move forward on that topic. And one last one just to point out, in the testing pyramid for verification, the wind standard is very much focused on material coupon testing at the bottom of your pyramid, and then full-scale blade tests to verify your overall structure. Aviation is much more focused at the intermediate level of sub-assemblies and subsystems. Wind is actually moving more towards that process, because blades are now so big, 100 plus meters long, it's hard to test a full blade for a full fatigue life. But it's an area that is treated a little bit differently. So I'll wrap up there, it's about time, and just point that future work is to kind of continue this assessment of the composite structures and composite processing side, but there's work needed to maybe in the short term look at what's required for prototype certificates following the IEC standard as the sort of lightweight version of starting this whole process, and maybe continue that gap analysis for production approval or organization approval, and ultimately for project certification and how that would look for airborne wind energy systems. So thank you all for listening to
Thank
a
you.
quick run through.
Are there any questions? Christian.
Thanks very much, and it looks like really detailed work there. Do you see already who could be, when you go into certification, who would lead, or would it be by topic? You basically have to change, okay, this time I go the IEC route, this time I have to go to the others, and or can this be somewhat combined in a body that does it all, or how do you see it?
Yeah, like if it's the IEC route you're going to take, then a group like DNV or UL or Bureau Veritas would sort of be the certifying body. Like if there's an IEC standard, that's the approach you're taking. They would likely maybe want to defer on specific topics like damage tolerance to experts in the field and bring in maybe some of the ASA expertise. But yeah, if you're going through that full process of type certification, it's all going to be through that body. I don't think you would be, I don't really see how you would be going through both in parallel. That would be my understanding anyway.
Thank you. Another question? Yes.
Thanks. Really important topic. Is there anything specific you can see related to tethers that's missing in the certification?
Right. So we were just focused on the aerostructures because it was, well, the project is wider and around material testing and manufacturing, so that was kind of our area of expertise. Say one topic that did come up was say the root attachment section for in the standard for wind turbine blades. Obviously, there's no direct analogy for airborne wind energy systems, but maybe a close analogy would be at the tether root connection. So there you're maybe seeing an area for overlap, but like the actual topic of tethers by itself would be worth referring back to that DNV mechanic analysis, because they do note that's a gap in the IEC standard, and they make some recommendations of potential, I guess, I don't know, cable tether related technology standards that could fill in that gap. So we were a bit narrowed down into a specific topic, but it'd be a good reference to check on that.
Good. I think we need to stop here also. So thank you again, Edward.